Okay, the second presentation is a silver nanowire integrated pressure sensor by Nathan, Nachiket, Peter, and Bryan.
Good morning, everyone. First, I'd like to thank you all for coming out to this presentation early in the morning and attending this talk. My colleague Bryan and I will be presenting here our silver nanowire integrated pressure sensor. And so I'd also like at this very moment to mention Nathan and Nachiket, who are also members of our team who have contributed to the success of this project. And so I think we can briefly start by talking about this device itself and how we got to fabricate it and all the device principles behind it. So I guess the overview of this presentation is that we'll be looking at the design motivation. We'll be talking about the device physics as to how it operates, and then some device fabrication, including the achievements that we received over the past 8 months. And then I'll be passing it off to Bryan, who will be talking about the software integration and how we were able to get actual readings. And then we'll end off with the conclusion. So design motivation. Why and what would we be exactly looking for in this, and what would be our actual problem? So we decided to create a pressure sensor because there's a known issue of pressure ulcers and bedsores in patients who are actually bedridden in hospitals. So these bedsores are usually located in the lower back region, and they come from the fact that patients spend a little too much time once they're after surgery, let's say, in their bed, and they can get these pressure ulcers, which can be very, very damaging to their health. So approximately 31% of these bedsores are created on the lower back region, and so as a result, it just causes more pain to the patient itself. And I'll talk about the money now in terms of how much it's actually worth. So in the US system, it's approximately $9.1 to $11.6 billion a year that the actual hospitals will have to spend maintaining these patients. Now, this cost is just derived from having to use medication to treat these bedsores, also the lowering the amount of resources that the hospital can now utilize for other patients and for other surgical operations. In addition, you have to incur the cost that the maintenance that they have from actual nurses who have to take care of these now patients additionally. And so as a result, you can see where this cost adds up. It is also estimated that in Canadian hospitals, this amount occurs to approximately $1 million a year that they'll actually have to spend on treating this. So as a result, we decided to investigate a solution to this to act as a preventative device for such a problem. So what's our solution? Well, we decided that we would be creating a flexible, biocompatible sensor which will be utilized on the human skin. And one of its primary functional capabilities is that it will be able to detect pressure on patients. Now, I'll get into more detail about that. But one fundamental feature that we wanted to examine in this case was that we would be able to deliver an audible cue, some sort of device, some sort of noise, once upon a certain threshold pressure has been, let's say, achieved for a given amount of time period. And so as a result, this audible cue will notify either nurses or the patient themselves to move over their position and to prevent essentially the bedsore from occurring. Now, one other aspect that we wanted to examine is that we wanted to be able to span different regions or different areas of the patient. So not just the lower back region, but let's say the knees. So as a result, this was another key solution that we wanted to implement in our pressure sensor. So obviously, when you're designing projects, there are certain sorts of criteria that you want to meet with your actual pressure sensor. We decided that these 4 would be applicable to our case, and we wanted to create the best and most optimal design. So firstly, flexibility. We wanted this pressure sensor to be flexible in comparison to other pressure sensors, such as like a simple scale. And so flexibility is the main issue because obviously if you're using it in a patient or let's say on a bed, the pressure or the force applied will not be uniform. So you want it to be able to deform, and as a result also not be able to, not have to go through degradation of performance or loss in its application. So secondly, we want it to be biocompatible. Now, why do you want it biocompatible? Obviously, you want to use materials which will be completely okay with touch of human skin and pose no hazards to the actual human or patient currently using it. Thirdly, one important factor that we have to consider is scalability. Now, why you want to consider this is because you obviously want to make this essentially a large area device. So you can fabricate many at the same time and compete with current strategies or current technology, state of the art. And then lastly, we want it to be ultra thin. Now, this is also another important factor because if you're going to use it in patients, you don't want to increase any of the discomfort that they have but essentially still get a pressure out of this and for its function. So here's our design proposal. We have two figures here. On the left figure, we have our actual pressure sensor when it's fully fabricated in operation. Now you can see here that we have, I can briefly tell you the three different materials that we have. We're using a PDMS, which is polydimethylsiloxane polymer, and then a dielectric layer, and also silver nanowires. Now, why are we using silver nanowires? I'll tell you that it's very important because it's a very simple process to create the conducting medium. So essentially what we have in our design fabrication is we have this three-layer structure similar to a McDonald's Big Mac, where you have 2 and 3 different layers, one which consists of PDMS. Now, what we do in the simple fabrication is that we drop cast our silver nanowires onto a silicon wafer. Then we spin coat the PDMS on top of this, and we let it cure. Now, once you peel this PDMS off, you essentially get a matrix filled of the silver nanowires embedded onto the top surface of the PDMS. Now, obviously, we use a concentration where these silver nanowires can intermix and create this conductive pathway for electrons to flow through. So then what you have to do, the next step, is to spin coat our dielectric layer, and then just form the top one. Once we have these two different substrates, just place one top and allow it to cure. And as a result, you'll get this sort of parallel plate capacitance. Making sure, now one important thing is to make sure that these silver nanowire conducting pathways line up so that we can get, let's say, like a parallel plate capacitor. So what are the functional requirements that we had to meet that we thought were very important for this? So first of all, we wanted to make sure that it would withstand approximately 1,045-degree bends without degradation in performance. We actually tested this, and we saw that there was absolutely no degradation and that the device was functioning. So for example, the device I showed in the previous slide on the figure left, that device has been basically fabricated 2 months ago, and we've been testing and doing multiple stress tests on it, and we actually achieved this target goal. Now, one other important thing, as I said, was the ultra-thin capability of this pressure sensor. So our original target was to make it 3 millimeters in thickness, which is almost barely noticeable. But actually, once our final optimization came in, we were able to achieve actually 1 millimeter in thickness, so almost a 300% reduction. Now, one other important feature that Bryan will be talking about later is we wanted to measure capacitance with less than a 5% degree of error for this pressure. And so now this will be actually moving into the device physics so you can understand how it actually functions. So the working principle of this, like I said previously, is that you measure a capacitance and you determine a pressure based on this capacitance. Like I mentioned, we have a 3-layer structure where essentially we have a parallel plate capacitor, and that's the formula on the top right, which is basically defining how this function operates. Now, when you apply a pressure on this, let's say, steady state capacitance, it'll change. This applied pressure essentially changes the distance gap between the different silver nanowire lengths, or the path, the distance, and as a result, a capacitance value will change. Now, here on the middle formula, we have the capacitance, let's say, for that sort of device right there. And then on the bottom, we actually have it that the strain actually relates this to the original capacitance at the steady state value as a function of an applied pressure, which we back out and actually calculate in our Arduino. And as a result, we can generate pressure values. So now I'll be looking just at some brief device fabrication and achievements that we received over the past 8 months. So we had a first generation device here that you can see, and you can notice that there are many major wrinkles which were appearing in this case. Now, this obviously came from, we noticed that it was the dielectric layer. We weren't spin coating it, but we were actually just drop casting it and allowing it to cure over a time frame. Now, one of the issues that we had with this was the fact that the dielectric layer started curing prior to actually all of it being uniform. So as a result, you'd get air gaps and voids within the actual structure. So as a result, it would crinkle up, and as a result, we can't get a very flat pressure sensor. So we investigated this, and we decided to use a technique of actually vacuuming the solution prior to actually dropping it and spin coating it, and also the spin coating procedure itself made us thin down the actual layer itself, and as a result, achieve our target of 1 millimeter thickness. Now, one important thing that we noticed with this was that we needed to make sure that this actual silver nanowire PDMS, let's say, top surface layer was conducting. So how did we do that? We used an RLC meter, and we applied a certain voltage bias across, and we noticed that we could get resistance measurements at different parts of the device itself. This was important to us because we made sure then that it was actually conducting, and one important feature of silver nanowires is the fact that they oxidize relatively quickly. But we absolutely noticed, like I said, no issues in our performance because we quickly, as soon as we fabricated this, we were able to encapsulate them in the dielectric layer and preserve their original state. So once we had this device made, we just had to complete the complete sandwich structure, and we attached electrodes. We used silver conducting paste and copper conducting electrodes. Now this would allow us, as a result, to connect it to our Arduino, which Bryan will be talking about, and essentially we would get the capacitance measurements upon a voltage bias being applied between the top and the bottom plates. Now, we achieved these capacitance measurements, but we had to optimize a little bit of our concentration of the silver nanowires used, and also then we had to make sure that all of the spin coating procedures and alignment would be perfectly fine to get this capacitance. Now, I'll be passing it off to Bryan, who will be talking about the software integration of it.
Thank you. So we decided to make the project complete, not just make the actual sensor. We wanted to also be able to create a prototype software package that could also read it out and do data analysis on it, because that's very important. It also helps with troubleshooting. So this is kind of the overview. We have a pressure sensor that Petar just outlined. We grabbed data from it through an Arduino, which we programmed ourselves to pull out the capacitance. We also, then two things happen. First of all, it gets immediately put into a database. That's important. Technology-driven firms need to have data management. And also we then do a real-time signal analysis, which you can actually see. You can come outside, and as you press it, signal responds in 1 second. So it's quite cool. The change in capacitance is very fast. So why do we choose an Arduino? Arduino we chose because, first of all, it's cheap. It's only $50, so that's nice. Second of all, there's a lot of online community that you have development code for it, so it makes the development process quite fast. And also, this is our circuit, so actually we replace our capacitor that we just explained with that capacitor right there, and that's how our device operates. So we actually calibrated the signal processing with a known capacitance value to see what our percentage error was, and it was 4%, and we targeted 5%. So we were within the error on that. All right, so the database we are using was MySQL. Again, it's open source, cheap. Of course, it's free, essentially. And then there's also a Python Arduino API that's available. And it makes it extremely easy for Python to grab the data directly from their Arduinos. As soon as it pulls it in, pushes it straight to Python, and then we use MySQL DB, which is a data visualization tool for database development. A lot of times when you're doing large-scale software development, sometimes visualizing the database can be extremely important, and MySQL DB is a great tool to use. There we go. All right. So the expected results, as we're saying, increased pressure, we expect a larger capacitance as the D is decreasing in between the layers. The actual results were not the expected results, of course. So we wondered, did we make a mistake? So I'll give you an example of what happened here. This is our results for 5 minutes. We have a quite stable baseline, and then 4 pressure points. And if you notice at the very top right, it goes back to the same baseline, so the hysteresis effects are essentially minimal. The capacitance is decreasing. This was exactly opposite of our expectations. When you press the device, the capacitance drops considerably, and then if the small pressure was a finger and the large pressure was like literally your entire hand we were pushing on the device. So why is this happening? We did a literature review on it because we were very confused at first, and this is what we attribute the kind of non-expected results to, is the fringing capacitance on the device. So our finger is right here on the right, you can see. When you put it close to proximity to the device, it shunts the electric field around the device because it's a grounding medium. So what essentially happens is that reduces the capacitance. That reduces the capacitance more than the gain you get when you press the device. So this is why in the previous slide you're seeing a drop in capacitance. We attribute that to this actual fringing capacitance field. So how do we get around this to show our device actually works? We used a water droplet. We put a water droplet on this silver circle that you saw in the previous figures. And this is what happens. So not a completely linear increase in capacitance, pressure, but you do have an increase in pressure as you add more water. And you can we backed out the weight of the water and the pressure of the water based on how much the density of water. So we added a milliliter each time. So these are the results we expect, but we only got them with water, not with the actual pressure of a finger because of the capacitance field. So some future directions that we think will fix that problem is, first of all, make the device smaller. If you have a smaller area, you're going to reduce the percentage effect of that fringing field. Another thing that we wanted to do is we want a nodal arrangement. We think this would be cool for pressure localization. And then we also want to create a full user interface that right now the interface we have is built strictly in Python and it's not interactive. Besides the real-time signal. But we think a full interface would be great for a hospital software system. And then also scalability is we'd like to dilute the nanosilver solutions and see if we still get the same performance. This could help reduce costs. And is the most expensive part of it. So what have we done? We met the lightweight pressure sensor requirements, and we basically have a working pressure sensor, and we demonstrated it working using water droplets. Now, we have the software, we've developed many iterations of the device, and we have achieved a 1-second signal response time. And we can set it for you outside to show you the response time. It's quite immediate, so it's pretty cool.
Thank you.
Now the session is open for questions.
So what would be the next steps for you guys then? Would you be looking to deploy this in an actual clinical environment, apply it to a patient that is actually like that?
So we were thinking the next step was, first of all, on the actual size of the, where does this go to a picture of it?
It's probably
I
back.
want the actual, this.
Yep.
Okay. So we were actually thinking of decreasing the size of this, the area, making it smaller, and then we'd put it in, for instance, we were saying put it on a bed sheet originally, and then have patients try it out, because we hope decreasing the size will reduce the problem we had.
The fringing capacitance.
Fringing capacitance, and then if you put it on a bed sheet, it's easier to do initial measurements because it's not going to be like moving with the patient. It's just going to be stationary. So that was what we would do next.
And just like we mentioned in our conclusion slide, we were hoping to do nodal arrangements. It was like one of our final target end goals, which in essence you would have, now instead of, let's say, a circle, you'd have multiple lines, and then you'd basically have an array. Now, wherever these lines essentially meet, and a pressure change happens at that, let's say, specific node, you'd be able to calculate or back that out. And as a result, you'd have a very nice spatial arrangement, and it would be able to. Exactly.
Yeah.
On specific positions.
Exactly.
That's where we would start.
Yeah.
I have one question. So, you have used silver nanowire for this material, right? So, can we use another material? And what is your opinion of using other materials, or what
Yeah,
is,
so it's the flexibility that I think that is the main issue. So the 45-degree bending was strictly because like if you use like a rigid paint or something, it's going to break the connections and you're going to lose the electrical contacts in the device. So that's actually why we chose the silver and nanorods, because they don't span the entire device and they have interconnections between them, so the flexibility wasn't an issue. And that's actually that's why we did the 45-degree bends, because it's quite a large bend. And a regular pressure sensor would break at that point.
Yeah.
If you go to slide 22.
32.
You said your measurement accuracy was plus 5% or so.
Yeah.
4%. The variation here is less than that.
For
Water, as we go for different measurements.
yeah, so basically, so I should clarify that. The 5% accuracy was, when we measured the capacitance, I think it was a 49 microfarad capacitor. We got it to 48 microfarads was what our reading was from the actual Arduino. So the,
And we keep on measuring it again and again. What is the
okay, so the plus or minus on that, yeah, it was much smaller, but we went from the actually just absolute, like how close is it, to what the actual capacitor value says it is.
Then my next question is, why is that important? Because you're looking for changes, right?
Yes.
Effectively.
Yeah,
Is
so-
there an absolute value really of importance of the changing design?
Okay, so this is related to the actual circuit design, which is why we, based on looking online, is depending on where your capacitance range is you have to use a different circuit. So the purpose of it was just to make sure our circuit actually worked for the around 60 picofarads, I think it was, that we were at.
Yeah.
84 picofarads. That was the purpose of that, because online there was some similar suggestions in research say if you use a different circuit, you might not get as accurate as an actual reading. Since we're using a change in capacitance, it would only affect the percentage change. So it's not going to be.
But exactly.
The next thing is, I'm not still convinced about your hypothesis about the finger.
Okay.
So if that would happen, if I bring the finger next to it and don't put any pressure, I should see a increase in capacitance.
Yes.
Correct.
And as I change the pressure, I should see an increase in capacitance. Because the finger is still there.
Yeah, so when you bring your hand near
Yeah.
it, it decreases.
Yeah, you can even.
And when you start pressing it, does it decrease or does it increase?
Okay, so it decreases to a point,
Yeah.
and then it doesn't decrease anymore.
Yeah.
But the increase isn't it. Basically, we're trying with our whole hand, and this is what we think the problem is why we have to make the circle smaller.
Essentially, the fringing capacitance effect over compensates for the actual pressure that you apply. Yeah. So essentially, you reach like a steady state where
Yeah, so
the
it's
pressure
like that.
you're applying is
It's
a certain
small
value.
change
Exactly.
compared to the
Yeah.
fringing capacitance.
Exactly. And it's interesting to note because this changes, at different, let's say, distances from the pressure sensor. So you can put your hand here and you
So
still.
how are you going to solve this problem? Because ultimately, you're connected to the
Exactly.
Use a smaller area.
Yeah. So one of, I guess, the techniques that we were brainstorming was to use a smaller area. Hopefully, because as a result, then your fringing capacitance fields will be smaller, and you can hopefully localize
If you
them.
use smaller area, the fringing capacitance fields will be actually larger.
But basically, what we mean is like you could calibrate them because your finger would actually like kill the whole the field around it. You're basically right now is when you put your finger on it or your whole hand, there's a difference. But we're thinking if you have just a little circle, whether your finger or your hand's there, it wouldn't make a difference because they're going to kill the same field, and then you
Yeah.
can calibrate it from the baseline. That's what we were thinking.
Those.
Yeah.
All right. Let's take the speakers.
One more.
Yes, so about the pressure, like one study can make this project more rich. If you study how deform the silver nanowires, like using console analysis or something like that, about the pressure and the strain analysis. Because what's happening here, if the pressure is too much, when I have a deformed area, so the overlapped area is going to be less effective. That's why your capacitance is less. So now my question is about something else. It's about the wire of capacitance connecting from your capacitance to the wheel. This wire capacitance is something range of 100 picofarad. So this
Yeah.
can affect all the result. Did you
Yeah.
cover this area?
Yeah, so we have a one outside where the arrangement's actually slightly different than the photo in here. Is like they're anti-parallel.
Yep.
So when you see, I see in photo.
Yeah, that one is like parallel. and that's gonna have
That
a-
one's in parallel, and then we had
Yeah.
multiple iterations where we did
We started
ones which
spacing
were
them.
completely opposite, 180 degrees,
Yeah.
and then ones which were at a given, let's say, angle,
Yeah.
to remove this capacitance, let's say, between the
Yeah.
actual wires. And we tested, and we also put in, let's say, we put in a PTFE,
Just to
and
see.
in between, the two, and hopefully that it wouldn't actually
see.
create a capacitance change, and we noticed that that wasn't the case.
So you